Good evening, everyone. Welcome back to the Astro Imaging channel. We have another great presentation tonight. Jon Talbot is here. We've had Jon on before. He always gives great presentations, and he has some very interesting targets to talk about and how to get to them. Before we get on to Jon, let me just give you a brief overview of upcoming shows, if I can. So I'm going to share my screen. Share my screen. Not that one, this one. Here we go. Yeah, we got some really nice shows coming up. Jon's tonight. Next week, Salvatore is going to be here. You all know Salvatore. We all have accounts on AstroBin, and he's going to come and tell us some of the latest developments. And there have been some interesting things happening with AstroBin. So that's going to be, I'm interested in it, and you should all be interested. After that, myself and Tim are going to do a presentation on imaging the upcoming eclipse. We both are going to be running automation software so we can watch the eclipse and still take all the images that you would like to have when you go to the eclipse. After that, Craig Stocks is going to be tell us about building an observatory. Nico is going to be there. After that, you all know Nico, again, another great presenter. So, and then we have, everyone's going to see the kind of images we got from the posted Messier 101 data that was put up there, and then the eclipse. And I'm excited about the eclipse. So stop presenting. Here we go. We're back. All right. Well, I don't have any more to say prior to getting Jon the floor. By the way, Jon has a very interesting background. I was going to tell you about it, but I'm going to let him tell you about it. But 34 years in the military, flying through hurricanes, crazy, crazy stuff. So the interesting and the calm part is all the astrophotography. Anyway, Jon, I'm turning the floor over to you. So go ahead.
Okay, great. All right, well, let's see if we can get this going here. Okay. All right, hopefully you guys can see my screen. Hopefully it looks okay.
Not yet. Oh, you see it?
Yeah. Just let me know when you, okay, are you seeing it?
Yep.
Okay, great.
We're seeing it now.
Okay, great. Well, thanks, Eric, for the introduction, and thanks everybody that's out there tonight. Thanks for letting me share about an hour or a little bit less of your Sunday evening. Yeah, I had a interesting career. I flew through hurricanes for close to 30 years, but I also knew when I retired I needed something to do, so I planned way in advance, and you know, started imaging about 20 years ago. So this talk is about sort of my adventures in imaging the unknown, and the unknown. What I mean about that is objects that are not well known. They're actually been discovered because there's coordinates for them, but maybe there's never been a picture taken of these objects. Maybe you know, maybe there's a picture out there, but maybe it's only black and white. Most of these are really faint objects, and you know, I started doing this a couple of years ago because I was getting a little bit bored after I shot you know, M31 for the 5th or 6th time, or M13 for the 10th time, and I wanted something of more of a challenge to myself. So the picture you see on your screen is I'll talk about this one a little bit later. This is called Pa J0637.4. It's a planetary nebula candidate, and I believe it's in Pegasus. But anyways, yeah, these are really faint objects, and you know, a lot of people ask me, well, you know, why do you do this? Well, because it's something different. It's a much more they're much more challenging than your typical bright objects, because these objects are typically faint. Not all of them, but a majority of them are. The other reason why I decided to do this is because I was trying to figure out, well, how can I help maybe the professional astronomical community figure out what's going on with some of these objects. You know, there's a lot of professional data out there, but most of the professional data is done with telescopes that have tiny fields of view. And, you know, we amateurs, we have systems that tend to have much larger fields of view, and we can see bigger things and see the bigger picture of what's going on. You know, I don't know how many of you knew that there's a planetary nebula right near the bubble. This is an image of this planetary nebula called KJPN8, which is really close to the bubble nebula, right up in this area here. This is the HA version of it. I didn't shoot O3 on this one yet, but there's a whole bunch of really neat O3 features in this nebula. And, you know, this is just an example of stuff that's out there that maybe you hadn't thought about before, and maybe you want to give yourself a little bit more of a challenge at not only the imaging part, but the processing part too. So that's kind of why I do this. It kind of keeps my brain in gear. It keeps me active. So a little bit about, you know, maybe what you need to have to do this types of imaging. Typically any scope's going to work, whether you have a large telescope or a small wide field telescope. They all work really, really well. You just have to kind of maybe pick your objects, you know, based on the scope you have. You know, with a long focal length scope, you know, those tend to work really good for small objects, and the larger objects for the shorter scopes. Most of the time, you know, you really should use a sensitive and low noise camera. But, you know, the wonderful thing about that is all our new CMOS cameras that are out there these days are typically very sensitive and low noise. And these latest generations of CMOS are excellent at doing this type of work. If some of you may have seen the presentation I did maybe a year or two ago about these CMOS cameras, you may want to go back and look at that. These are wonderful pieces of equipment to have these days. Typically, you're going to have narrowband filters of some sort. You know, 3 to 5 nanometer tend to work pretty well. By using narrowband filters, you know, you can do a lot of the work maybe in partially light polluted skies. So in my case, I live in a suburban location, and most of the work that I'm going to show you was shot right here from my backyard, which is a Bortle 5 sky. Color cameras, you know, a lot of people say, hey, can I use I have a CMOS camera, but it's color. Well, there's some really cool dual band filters out there these days, and some wonderful presentations on YouTube. Just search YouTube on how to process an SHO or a Hubble type palette image using the dual band filters, and you'll find a whole bunch of just fantastic presentations on how to do that. So yeah, you want to have narrowband filters of some sort, because most of these objects are, you know, show up in as emission type objects, and the narrowband filters definitely help bring that stuff out. The other thing you need is a lot of time. These are really faint. These are you know, extremely faint objects. Maybe you need to spend something like 30 to 60 hours on some of these things. I typically average about 40 hours from home. The nice thing about having a dark sky is you can typically get by with less exposure time to get the same type of signal. And usually it's probably something like I have to expose at home probably twice as long to 2/3, you know, twice or more compared to a dark sky. So, you know, maybe in a dark sky you're shooting 20 hours, and in a suburban sky you're shooting you know, again, 30 to 60 hours. But yeah, you need to have some time. But if you have time on your hands, and if you have a setup in your backyard, you know, you may have a lot of time. And you know, to me, I've got time. You know, luckily, I'm fortunate to have a setup in my backyard, so I don't have to, you know, travel to places. And it's a little bit tougher if you have to travel, but this may work out for you in this case. So that's a little bit about maybe what you should have. And I'm not going to go too much into processing these things, only to kind of highlight a few things. Typically you do standard calibration and creation of your master frames. You're going to want narrowband exposures, HA, oxygen 3, possibly sulfur, and you're going to want RGB exposures. Typically we're going to use the RGB exposures for the stars, and they provide a nice, beautiful star colors to a narrowband type image. You also need to learn how to continuum subtract your narrowband masters. And, in the sky, we have gazillion stars, and those stars emit light in whole bunches of different wavelengths. So what we need to do is subtract those wavelengths of light from our narrowband images. So all we're left with is the emission signal. There's a lot of good tutorials out there on how to do that. It's a little bit of a trial and error, but for example, you subtract from your HA images the continuum light from like a red master frame, and you don't necessarily subtract all of it, a certain percentage of it, but that's kind of like the idea, and that leaves the emission signal, and you're really seeing what the object looks like in that narrowband light. A lot of times we find that broadband light will actually leak into these narrowband filters, even if you're using like I use 5 nanometer filters, and broadband light gets in there, and it's amazing how much gets in there in 30 or 40 hours. So yeah, you need to do continuum subtraction, and I'll let you guys go out there and look at the tutorials on how to do that. And what you're going to do is process the remaining narrowband color channels your favorite way. Everybody has their favorite way of doing that. And normally we do this as starless type images. And there's some wonderful, apps out there now to remove stars using AI. And they work wonderfully. And you want to have one of those types of ways to do that, because you basically are going to process images in the narrowband color channels without any stars, and then you add your RGB stars in. So then you get a pretty cool looking image. So that's kind of like the basic overview of how a lot of people that are out there doing this type of work, that's how they process their objects. So in 2021, I kind of became interested in this challenge to do this. I imaged a lot of stuff over the last 20 years, and I was looking for something different. So, AstroBin being such a wonderful resource, and you'll hear a lot about that next week, there was a whole bunch of objects I saw that popped up on there that I had no idea what they were. I was like, holy cow, what is that object? I never heard of that one before. And I started looking on AstroBin and writing these objects down and figuring out where they were. Here's an example of this planetary nebula called HFG1, Hecathorn Feacen Gull 1, and another planetary nebula, Abell 6, down there in the lower left-hand corner in Cassiopeia. This was a really faint object that was discovered in 1982. And it's got a really cool tail of HA that goes down into the right from it, and it's got a burst of oxygen 3, and really neat object. This is one I saw on AstroBin, and I thought, you know what, I'm going to give that a try. And here's an image of it from, I was able to do from my backyard. So that was kind of cool. And that kind of got me going, but it wasn't the first one. And the other thing I was thinking about, where do these folks get these targets from? So I started emailing some people and asking some questions, and lo and behold, there are databases out there that have these types of objects in them, and I'll show you some examples of that in a little bit. So the first one that kind of got me going was this object called FR2-25. And let me just say something about the designation. So in this case, FR, well, that stands for Dr. David Frew. That's the first two letters of his last name. And most of these objects are named that way. You'll see objects that have all kinds of different letters in these lists. And typically it's the last name of the individual that discovered them. This particular one was discovered by David Frew in 2008. And also at the same time by amateur astronomers, Philippe Alvis and Matthias Kronenberger in 2012. And I shot this in 2019 from my backyard. And this is an ancient planetary nebula that I happened to just find by accident on the internet one day. And I thought, let me give that a try. It looked like it was about the right size. And lo and behold, there it was. And you can see it's got some really interesting oxygen-3 signature to it. It looks like a half a moon. There's a little bit of hydrogen in there, but it's mainly, more O3 than anything else in this case. And, it was extremely faint. I spent a lot of hours on this, 25 hours. But that kind of got me thinking, you know what, if I put 25 hours into this faint object, there's a whole bunch of other faint ones I bet that are out there. And if I put a little bit more time, I bet you I can, detect them. Well, an individual, his name is Saqib Rasul in the UK, saw this image and he was like, he was wondering, how did you find this? And I said, well, I looked at this list and I found it on this. I found an image of it on this site. And by chance, he said, hey, I've got lists of stuff. Would you be interested in, a list of these faint, sometimes they're large, sometimes they're small objects, and I can send it to you. And I thought, well, yeah, that's exactly what I'm looking to do. So I gracefully accepted that invitation, and that kind of started my journey into imaging these things that really are not well known at all. Here's a look at what the narrowband versions of that object look like in HA and O3, and these are inverted images. So the stars look dark, but you can see in the HA image where a little bit of the the same crescent look to it, and it's got a little bit of HA off to the right hand side above it. And the signal in O3 was a little bit stronger, actually, a little bit wider. And when you put those together, you get that teal looking look to your image. So yeah. So moving on, Patrick 5. This is another one that was interesting. It's in Cygnus. I did this one in July of 21. It's really, really faint. It was discovered in 2005 by an amateur planetary nebula hunter named Dana Patrick. And he was scanning DSS survey plates. And he came across this thing. And, I don't, there's other images of this out there, and you can search for them on, sites like Astrobin and stuff. This was a bipolar nebula, and it's got really, really faint, HA. It's mainly an oxygen-3 object, but if you look in the center, the central star is blue, and typically most of these faint planetary nebulae like this have a hot white dwarf at the center. So that's what the kind of the meaning of the blue star there. This was a tiny one, about 2.5 arc minutes in size, and I put 27 hours into this, and I was trying to figure out, how long should I image these things? And I think I settled in on around 25 to 30 hours here from home. And your experience may be different from your site, but from my Bortle 5 sky, that's about what it takes. Maybe you could get by with 15 hours in a dark site, maybe a Bortle 2 type sky, or maybe even a little less. But this is kind of a cool object. Looks kind of like an eggshell. FR230, again, discovered by Dr. David Frew. This one is in Andromeda. And I put some good time into this one in September of 21. This was actually a little bit larger, about 23 arc minutes in size, and it had a designation already I was able to find, I believe in Simbad, I think. Yeah, PNG 126.7-15.4. If you took just an RGB image of this area, you would absolutely see nothing. You wouldn't know anything was there. So in this case, the narrowband data was an absolute must. And so this was, discovered by David Frew, and then also independently by a team, I believe in China, Juan and Lu. This is listed in this database I'm going to talk about a little bit later, called the Hash Planetary Nebula Database. And yeah, so this was collected in September and October. And this led to an interesting thing, which I never, thought would happen, but it did happen. It just so happened that there were some professional astronomers that took spectra on this object and were writing a paper about this. And they came across this image, and I don't know if they found it on my website or on AstroBin. I posted it in both places, but a gentleman named Dr. Howard Bond from Penn State University got a hold of me. He said, "Hey, we're writing a research paper on this, trying to determine what this object is. You have the first and only deep color image that was ever taken of this before. Would you mind if we used it in our paper, and would you like to be a co-author?" So that resulted in this paper, which was really, it kind of blew me away that, but at the same time, I was really happy because this is kind of exactly what I was hoping would happen, that I'd be able to help out maybe the professional community in some sort of way. So they wrote this paper. Of course, I had nothing to do with the science in the background, but I had a lot to do with the image. And it was ultimately determined that most likely that this is just some emission that's interacting with the interstellar medium and not really a planetary nebula. I think the jury is still out on this, but that's basically the gist of what the paper said. So, you could find yourself in this situation. There was no other images of this thing, and I just found this on one of those lists, and I thought, you know what, I'm going to give this a shot and see if I can see if there's something there. And lo and behold, there was. And so that's FR2-30. Moving on to another one of these FR objects. This is FR223 in Perseus. This one took a little bit longer, over 40 hours. And again, this was the first color amateur image of this faint potential planetary nebula in Perseus. It's pretty large, almost the size of the full moon. It has mostly H2, but a little bit of, you can see there's a little bit of a greenish teal hue in the center. That's the oxygen 3 data. And, whether this is a real planetary nebula or not, that's probably going to have to wait until professional spectra is taken. But you know what? Maybe one of the researchers that's going to take that spectra will come across this image, and it'll help them out in some way, form, or fashion. So I was, thrilled to get something here, because this thing was really, I mean, I had to dig real hard to pull out any data. And I'm not the world's best processor by any means. There are many other much better processors than me out there, but I was able to show it. So I thought, you know what, that's really kind of cool. Okay, moving on to a different object now. So this one's called Patrick Strottner-Dreschler 6, PASTDR6. Again, the name designation, PA stands for Patrick, ST for Strottner, and Dreschler DR. Close to 30 hours a couple years ago in January. And again, this was the first time a deep image was ever taken targeting this particular object. And you know, somebody may see this one of these days when they take the professional spectra, and it may help them out to determine really what this is. This is another faint planetary nebula candidate in Perseus. You know, it was discovered by Dana Patrick back in April of 2020, but also and I'll talk about the STDR team of Xavier Strottner and Marcel Dreschler. They also found it, and it's got a designation in SIMBAT of this PNG 148.4 09.1. You know, a number name. I think I like the PA STDR6 name better. But yeah, it's a beautiful object with mostly all HA. I didn't really detect really much in the way of any O3 here. There's a little bit of really faint O3 in the background, but mostly this was HA. So this was, you know, another one of those really neat things that, you know, it's also the excitement of when you process these things, because you know that no one's seen this before. You don't really know what it should look like. You know, you do your best to bring out what you can, and you know, when it's done, you post it, and there you go. It's out there for the rest of the world to see. So yeah, so there's PASTDR6. Okay. So I think my favorite of all time is this one here so far. STDR44. This is in the winter sky in Monoceros. I did this one in January of 22. And again, this was another one of these. This was the first time an image of this was ever taken. This was discovered by Xavier Strottner and Marcel Dreschler. And in 2020, it's really close to the Seagull Nebula. And I'd never, you know, I've imaged the Seagull a bunch of times in wide field stuff, and I've never seen it before. But, you know, it's the time you put into this. On the lower right of this, there's another little planetary nebula there that was listed in this database as, you know, possible. Well, because of my image of this, it was upgraded to a likely planetary nebula, I guess, until, you know, some spectra is taken. But, you know, it's a typical oval shell of gas. And the nice thing about being an individual that, you know, took the first image of something like this was I got to name it. And I decided to call this the Heart in Monoceros. And it's kind of like a heart on its side. You know, we have the regular Heart Nebula and so forth, but yeah, it also looks sort of like a heart. Here's a little bit more of a view of it. So I sent this data to this team called Team STDR. They're over in Europe, and Marcel Dreschler processed this. He did a masterful job on this. I mean, this thing is just beautiful. And sent me the data back, and you know, we posted this on AstroBin, and this was the first time anybody had ever seen this object before. Another team of professionals saw the little planetary nebula there, and they you know, saw the data on that, and that's where they determined they would upgrade that little guy to more of a likely scenario of a planetary nebula than just a possible, because of its morphology and how it looked. And it's got a nice little HA shell to the north of it, oxygen 3 in the middle. STDR44 has this heart shape to it with O3 in the middle again. And it's hard to see if there's a hot central star in there. I'm not sure. But yeah, these guys that actually put this together for me, that took the data to process it, did a wonderful job. And they've been doing this type of work for years. And I'm going to show you some of their stuff here in just a minute. But yeah, so this one got my blood going, and I thought, you know what, I think I'm hooked on this stuff, because you know, I had no idea what I was even looking for here. But it's got a nice little big area of HA to the south of it. Another little guy here, and I forget what this object is here. I probably had plates off all this, and it's probably listed, but I just can't remember what that one is. But it's kind of a beautiful area in the winter sky. So maybe somebody else can try their hand at this and probably get a much better image than I did. Yeah. Okay, this one is kind of interesting. This is PARAS Mommy 1. Again, that stands for Dana Patrick, Saqib Rasul, Sankalp Mohan, and Utkarsh Mishra. They discovered this in 2021. And I was able to image it and put about 35 hours into this. And it's kind of cool. It looks like a planetary nebula candidate. It's got a lot of oxygen 3. There's actually a lot of oxygen 3 in the whole area off to the left. Also, a lot of HA in the background. And yeah, it's kind of a neat object. It's big. It's close to the Rosette Nebula, and it's almost the size of the full moon. So in this case, my wide field setup was really useful. And a lot of beautiful stars around this area, and not a lot of people have seen this object before. This isn't the first time it was imaged, I don't believe, but this was just kind of like my take on it. And I had no idea what I was looking for, but when they asked me to shoot it, but yeah, it's kind of cool. Okay, my other favorite, this one. This is the first time anybody's has seen this thing. This was discovered by Dana Patrick, the Pa J0637.4 plus 3327 is the big name of it. It's another one of these planetary nebula candidates. It's in Aruga. This is the first time a color image has ever been taken of this, and it was discovered by Dana back in December 2018. And it's got a central star of magnitude 17. And I'm not sure exactly which one it is in here. It's probably one of these little blue ones, but that would be the central star. But a lot of oxygen 3, a lot of HA around it. Excuse me. And I spent 58 hours on this. And this was there's kind of a story behind this one. I've done some imaging for I produced a few images for the team over there in Europe and for Dana. And this was Dana's birthday that was coming up. And one of the individuals in Europe got a hold of me and said, hey, how would you like to take an image for Dana? We can do it for his birthday. And so I did it. And Marcel Dreschler processed this, and he did a wonderful job at it. I just can't get over how good of a processor he is. And so you're seeing the first image of this object, which looks really, really cool. So this one is brand new. It's out there. This is on AstroVin also. So if you guys, anybody else is interested in taking a shot at this thing, it's kind of faint, but it's in the, it's probably a little late maybe now. But it's in Auriga, and yeah, go for it. This is kind of a cool object. It's big too. So I don't know what Dana's going to call this thing, but yeah, kind of neat. Okay, back to Patrick 165. This was the image that I had in my first slide. This is a really tiny little object, and it's really faint. And hopefully it's it's another one of these planetary nebula candidates that's out there. This one's in Pegasus. And this was my shot at this thing. And I mean, this was so faint, I really had to dig to get data out of this. It has a lot of O3 and very little HA. You can sort of see a little bit of faint HA in the background. There was some really faint stuff right down here at the noise floor. And, I could have left this dark also. I mean, it's really, really faint stuff. But it has this kind of, kind of a oval shape to it with some striations over here. And the central star is right in here. This was also imaged by Kit Peak. And Kitt Peak has a 4-meter telescope, the Mayall telescope. So when you look at this image and then we compare it to this is the Kitt Peak image over here on the left. You know, I got a lot of the same features with my 152 millimeter versus 4-meter scope, but I got a much bigger field of view and a little bit of a different view of the surroundings of this thing. There's also a supernova remnant close to this, which added to the story of this image, G0700-21.5. It's over here, this HA region. It would make probably a really wonderful image to go further off to the right and image that supernova remnant, but I'd probably have to do a bunch of panels for that, a mosaic, because most of those guys are really large. But I got the general idea that, you know, a 4-meter scope, my image, you know, not that much different. I had to put a lot of time into this. Believe it was 44 hours. Yeah, 44 hours into this image, but it was still a lot of satisfaction as seeing something really cool for the first time. You know, I never knew that the actual discovery image from Kitt Peak was there, and that was sent to me after I, you know, published this image. So I was really happy that, you know, even my little scope, I've got the separation of these stars in here. Most of the same stars are showing up. There's a few fainter ones in the 4-meter image that don't show up on mine, but heck, you know, I'm doing this from a 405 backyard. So I was thrilled when I saw this one. So that's Patrick 165. Let's see, I probably have a few more here. This is one of my latest ones. I haven't published this one yet. At least on Astrobin, I believe it's on my website, but this was another possible planetary nebula called STDR-55. And this one was done late last year, November, into January. So it takes me about 3 months to get about 40 to 50 hours with the weather and so forth. This was discovered in June of 2020 by the Team STDR folks over in Europe. And this is the first deep color image of the object. Unfortunately, there isn't a whole lot of O3 here. There's a little bit of O3 in this other object off to the left called IRAS 01342. And this object has this really cool looking faint shell of oxygen-3. And I was wondering what that was. So I got a hold of the team over there in Europe, and they sent me a paper that this actually had been studied quite a bit in the past, and I was able to take a look at that paper and figure out what that object was. But STDR-55 is this little guy right here, very, very faint, surrounded by a sea of you know, hydrogen nebulosity. And there's a zoom in of it, kind of what it looks like. It's kind of like got fingers to it. Now, the team in Europe thinks this may be one of the oldest planetary nebulas that have ever been found, and they gave it a name of Methuselah. They mentioned to me that it's probably so old that it actually lost the oxygen-3 shell around it, so that's why we're not seeing a whole lot there. But again, this was kind of a neat discovery type thing, at least for me, because I had no idea what I was even looking for when I image this. And on a single image, you're not seeing much of anything, you know, until you put everything together. So I think this may have helped them determine, you know, what this object really looks like. And you know, hopefully the team over there in Europe will get some professional data on this, and it'll be maybe, hopefully in the future, a real planetary nebula. I guess we'll have to wait and see. Okay, so the other object off in the left-hand side, this IRAS object, it turns out that this object, you know, when I first saw this, I'm like, holy cow, I wonder if this is like another planetary nebula that no one's even mentioned before, because all the databases I found, I really couldn't find a whole lot about it until the European team sent me the paper that was done on this region. And it seems like this is called a maser object, which is a microwave type object that is, stimulates the emission around it, and it's really strong in infrared radiation. There's actually a little bit of O3 in this area. It kind of looks like a bubble surrounded by a bubble of O3, and some really, really bright HA objects right in near the center of this. And I mean, these were really, really bright. I really had to tone them down. They reminded me of like the Herbig-Haro type objects, where, star forming regions that were so bright. But that was kind of neat and as an image all by itself, because it was kind of one of these things that you just wouldn't see when you do normal imaging work. It's not something that you can just say, hey, I'm going to image this next time around. It just kind of happened to be in the image. So yeah, this one was kind of cool. And again, yeah, this will go up probably in the next week or so, probably an Astro bin. But I wanted the team over in Europe to see this first before we did anything else with it, and I believe they were appreciative of that. So this team that I'm talking about, it's called Team SCDR. They have done some wonderful work over the years. Most of the new discoveries you see in Astro bin are posted by these guys. They are a dedicated team of individuals that have found, I don't know how many objects now, just all kinds of stuff. You saw the, emission arc close to M31 last year. Well, that was this team. And when I say team, it's comprised of a couple individuals that do a lot of the background work, and then a whole bunch of amateur astrophotographers. I did a little bit of work for them, but there's a whole bunch of people out there that do work for these guys, and they produced some wonderful images and things that you have never seen before. I stuck my chest out and stuck my little guy up here, but all these other ones are just as fantastic. I mean, they're just wonderful, and you never know these things were there. So I guess, I would say to you folks that, especially if you're interested in doing something like this, if you want a challenge, these are challenging objects. I think I remember when this image here of this O3 arc near M31, this blew the professional community away, because they had never seen this, because they can't, their telescopes typically are too narrow fields of view to pick up this stuff. And there'll be a lot of work coming in over the next bunch of years to determine really what this is. A lot of these objects are exciting to the professional community, because they, especially the folks that are working in the planetary nebula field. But not all of these are planetary nebula. There are other things out there that are sort of maybe undiscovered in a sense. So where do you find some of this stuff? Well, here's a website called planetarinebula.net, and it's a French website, but they do have an English version of it. You just click on the little British flag there, and you get English. You can find in here all those objects that I just mentioned are listed in databases on this site. There's stuff about, hey, what if you come across a new object? How do you announce it? How do you send it to somebody so they can look at it? There's a whole bunch of really cool links here. Right now they have 400, well, at least when I did the screenshot here, 400 unpublished planetary nebula candidates out there. So there's a whole bunch of stuff that you could image and probably last you a lifetime. And you can access the list very easily. Here's what the listings sort of look like. These all go by the names of the individuals that discovered them. So like the STDR stuff that I did, well, if you clicked here, you get a list of all these STDR objects. If you clicked here, you get a list of the PA STDR objects, all the stuff that was discovered by Dana Patrick, Xavier Strottner, and Strottner-Dreschler. The mommy objects. I did one of the mommy objects, and well, this is all their stuff. So you can click in here, And then you can get those, a listing of these objects, the right ascension and declination, and the size of them. And so you can kind of weed through those and until you find something that maybe fits your field of view that you have. Most of these are going to be kind of faint. You need to spend a little bit of time on them, but there's a world of stuff out there that I never knew existed until I started imaging these things. And this is just one of the websites here. And again, if you are watching this on YouTube, you can watch it again tomorrow, and you can get the, here's the link on how to get in there. Here's kind of a listing of what it looks like when you pull down a list of these things. Here's the PNG designation, the RA and DEC, the size, and what they are, at least what they think they are. And I bet you a majority of these objects, there aren't a whole lot of images out there of them. You could be someone that produces the first image of a lot of these things. So take a look at these lists, and you may find something that fits the time of the year it is and your system's field of view. So there's another database out there, and it's run by the Hong Kong University. It's called HASH, Planetary Nebula Database. And it's sort of similar. You have to sign up for an account for this one. But they, you can cross-reference objects by typing in a search. It pops up with something like this. Here's that FR223 object that I imaged, a year and a half ago, kind of where it is. It gives you a designation of other images that are out there. You can, it'll show you some professional stuff if stuff's available, a little bit of an idea of what the object is. And here's an example of, when I imaged this object, in the notes section, the folks that run this threw in there a link saying, hey, here's a brand, deep amateur image of it, and this was my website image that I posted. So, this to me was great. This is a way that us amateurs can really help out the professional community. And it didn't necessarily change what this object is, but it threw out to other professionals, hey, here's a nice color image of this thing. If you want to take a look at it, here's where you can find it. So that's the HASH Planetary Nebula Database. And it's another great resource of, it's not a listing like the planetaryNebula.net. It's not like you can click in here and just get a list of objects, but you can cross-reference an object that you're looking for, or maybe that you're going to image, to this database, and you may find some professional data on it or some other notes about that object. So it's really good for that, for sure. Okay, well, let's talk a little bit about other stuff. Well, there are supernova remnants out there, and if you've seen some of the work done recently by the STDR team, gentleman Bray Falls, another wonderful imager, they've done some wonderful work on supernova remnants. Well, there's a list for that too. And here's just one example of that. And you can, this listing, I believe, is about 300 supernova remnants with where they are. And you can click on other documentation in here to get some other ideas of what they think these, what they're made up of. Maybe when the supernova actually happened. And there's cross references over here of other names they go by, but this is a huge listing here of that type of stuff. So maybe that is something that would interest you, to look at supernova remnants. And these things are usually pretty large. They take, large fields of view. A small telescope that's fast with a nice sensitive camera would probably do wonderful work on a majority of these. So here's an example of that. So recently, just a couple months ago, I was imaging this object called NGC 559. It's a star cluster. And this is what the RGB image looked like. And I kind of got a hint that, hey, there's a supernova remnant in here. Maybe you can pick it up on your wide field of view in the HA. So I took my normal, 30, 40 hours worth of data. Here's 27 hours of HA data on this object with the stars. Here's that little cluster up in here, NGC 559. When you take out the stars, all of a sudden you get a different look of this object. And when I looked at this, I must have stared at this for a couple hours. I saw this faint oval type shell here. And, I could trace it all the way around. And I started thinking about this. What is that? And I really started doing some homework on this because I was thinking this is that supernova remnant that's in this area. It was very close to this cluster. So what I was able to find was this is radio data, and I was able to overlay that on my image, and the edges of this radio data followed the edges of my HA data almost to the T. This was a paper that was written a while back. The most recent one, I believe, was from 2014 here, where the individual showed that there was actually a signature of the shock front in this curved band of HA here, which is the shock of the explosion, creating this curved area. Well, that showed up really well in my image. I mean, this is my image in the background here. And I sent this data off to several professional astronomers that were working in supernova stuff, and they were pretty convinced that most likely I was able to see the actual image of a reflection of this supernova in HA. And there had been one other attempt at doing that professionally back a while back when CCDs were very popular, and they didn't show much. Whereas my image, I believe, showed quite a bit. And so I think I'm pretty sure that I've got the first probable, look at the reflection of this in HA. And here's a little animation. I think it's going to run. Let's see, maybe it won't run. Yeah, here we go. It's going to run through the HA, and then we're going to overlay some of the other data on here. That's the continuum subtracted image there with the stars. And there's the some radio data overlaid on it, and other radio data. And then the most recent paper showing that molecular cloud. And this is what I think we're seeing here, the shock front of this explosion. And I believe that's the first time any amateur has been able to show that. Now, right after I did this image, I found the team over in Europe, the SCDR guys, they were also imaging this at the same time, and they had no clue I was doing it, and I had no clue they were doing it. And they produced a wonderful image of this object. They added S2 into the mix where I didn't. And they even got a stronger, I think, representation of the actual supernova remnant. But yeah, this is kind of exciting stuff because you never know what's in your stuff until you start really deep diving and looking into it. And, you pull stars out of these images these days using these wonderful AI algorithms, and you see stuff that you had no idea that was actually there because the stars were kind of creating a confusion. So, so hopefully, stuff like this, and the other image that was even better than this that was done by the SCDR team will help professionals, figure out what these things are. So I spent about 50 hours on this thing, and I think, it worked out really, really well. Okay. So that's, I think, I got a few minutes for questions. That's the end of my presentation for you guys tonight. There's my contact if you want to get a hold of me. And I will turn it over to the guys running the show to see if maybe there's some questions out there.
Yeah, Go ahead, Alex. There are a few.
There are some questions. Why don't Eric? Oh, you wanted to ask something first? Go ahead.
No, go ahead. I just I thought we were going to have a pause.
Let's quit
Go ahead.
fighting and get on with this, John. The first question is from Alex. That's me. When we were back talking about continuum subtraction,
Yes.
you mentioned that you needed to do both RGB and narrowband. Why do you need the RGB?
Okay, so when you continuum subtract the continuum light from your HA, say, you need a red image to do that. When you continuum subtract the light from your oxygen 3 image, which is right in the middle between the blue and the green wavelengths, you usually use something like maybe a mean BG type image, an image of your blue data and an image of your green data that's kind of averaged together. And that's what's subtracted from that oxygen 3 image. So to subtract the continuum light, you need the broadband images to do that.
Okay.
Does that make sense, Alex?
It makes sense, but why do you need, if you're shooting a narrow band, I use 3 nanometer narrow bands.
Mm-hmm.
Aren't I after the narrow band color, and isn't that what I'm already getting?
Yeah.
So why do I need to subtract the standard red?
Believe it or not, broadband light will get into your narrowband data. It happens all the time.
Okay.
And it leaks in there somehow. I don't know how it leaks in there, but when I was doing some work with that team over in Europe, they mentioned to me one time, because I sent them some data. I said, hey, I think there's signal here. And they came back and said, nope, when we continuum subtracted this stuff, all you were seeing was broadband data that had leaked in somehow, some way through your 5 nanometer filters. And it's apparently a common thing. So by doing this continuum subtraction, you get rid of that. And what's left over is just the pure emission.
All right. Tom and Isaac and various people throughout the presentation said, okay, like what kind of stuff's this guy got as far as equipment? What's he using to show us these pictures?
Okay, so I'm in a light polluted area, Boreal 5 sky. I use a 6-inch refractor and I shoot at f8. Not it's not fast by any means, but I have a very sensitive camera. I've got a ASI 6200, same as the QHY 600. It's one of the later generation CMOS that are very sensitive and low noise. And I think a lot of the success in doing stuff like this has to do with very low noise cameras, because noise messes up a lot of detail. And if you can get rid of the noise, you can start seeing stuff. So that's why, and I use a Paramount Mighty, but it's not any, it's not a mount that's, there's lots of wonderful mounts out there. So I've got just I use a fairly slow scope, but a very sensitive camera, and I spend a lot of time, and that's a lot of it has to do with the time.
Did you mention your mount's name? What mount?
I have a Paramount Mighty. It's the small little Paramount, that little robotic mount. But
thank you. Jax wants to know if you do find an object out there, not because you've been searching for it and managed to get it, but just in your imaging, you find another object out there. How do you know if somebody has discovered it before you, or how do you know that you're the first discoverer?
Yeah, that's a great question. Well, there are several ways that you can go about this. You can search you can search on Astrobin. You can search there's several NASA sites out there. There is the hash database, like I mentioned. You can email other people that have, you may come across a really cool image of some faint stuff or a discovery image on Astrobin. I would email those people and say, hey, I think I found something here. How do I go about finding, more information about this? There are folks out there that are really willing to help anybody, if you think you came across something. On that planetary.net, planetarinebula.net website, there are specific procedures that they have outlined that if you think you found something like a planetary nebula, who do you get in touch with? Well, those same types of people can get you in touch with other types of people if you found something different. Like when I found that, when I had that other, what turned out to be a maser object, I let that team in Europe know about that, and they said, "Oh, this has already been studied." I had no idea, and they sent me the paper on this. You can search. It's amazing how much stuff's available online. The professional research papers. So there are ways out there, and you basically have to do a little homework and digging, but you can find something if you put some effort into it, for sure. You can find somebody that knows.
Okay. Tarek wants to know, how do you find these objects if they're so faint? He's particularly worried about maybe spending all 50 hours collecting data for these objects and finding out that there is not, in fact, something there. I imagine it's wrapped up with plate solving and centering or something, but what actually happens?
Well, you don't know. Maybe you don't see anything. I've shot, I don't know how many objects now where there was absolutely nothing there. And it's the risk you take, but the reward is just as good if you actually do have something in your data. That's kind of like the excitement of it.
Well, it's not as if you tell your scope to go there and just start taking pictures. I mean, you have to know some coordinates to go to.
Right. So
your scope has to be set up so that it'll go to those coordinates and prove that it's at those coordinates before you start imaging. And then you might not succeed because it is just too darn faint.
Yep. So you have coordinates, and most all automation type, whether you use something like Voyager or Nina, a lot of people use Nina these days to automate their imaging. There are other software out there. Typically what those pieces of software do is when they point to something, they take a plate solve image and they figure out where they are in the sky. And if it's not really where it should be, well, then it adjusts your mount. So usually the coordinates that you have for a potential object, you're going to be at the right coordinates because your image is going to be plate solved. And if it's not, you can plate solve it after the fact and determine where you are and where that object should be within your image frame. So plate solving goes a long way at making sure you're in the right spot in the sky. And your typical guy that goes to a star party and wants to take some images during the week, probably this stuff is not going to be for you. But if you have like a setup in your backyard, or you have some time on your hands, then but the excitement is you just don't know what's there all the time. Sometimes you just not until you start processing it do you actually see anything.
Okay. Your Pet Chick 165, was that color or mono?
That's color image.
Wow, because it was very low intensity color. It wasn't very saturated.
Yeah, that's a super faint object, and I'm not one to oversaturate things or really boost it up. There are other folks that make images look a lot better than I do, but so that was mainly oxygen 3. That was kind of a teal color.
Okay. Isaac wanted to know, during background extraction, how do you tell the difference between those faint unknown objects and the background?
Well, typically, so you create a starless image, right? When you do continuum subtraction, you want to start with starless images. And so maybe I have a starless red image and I have my starless HA image, and I subtract that red image from the HA. What's left over, if you see something there, and you have to stretch it pretty hard, what's left over is most likely, either that object that you're looking for, or what's left over is emission data, and that's probably it. And these things are really faint. Sometimes it takes a lot of work to bring them out, a lot of stuff like noise reduction and stuff like that. So it's not processing for the faint of heart, for sure. It's takes a little time and to put these together. But yeah, sometimes you may not see anything in the background. It's hard to tell sometimes. But usually you can really stretch them hard on your screen and you can tell if there's something there or not.
There's some questions that came in after you concluded your presentation. Isaac wants to know, what do your unprocessed master frames look like? How noisy are they? What do the gradients look like?
Yeah, so I have lots of gradients. I have great gradients in my east and west. So to be honest with you, I use PixInsight to process most of my stuff, at least to get the masters done anyways. And I use dynamic background extraction to get rid of the gradients. And obviously, yes, you have to get rid of them. You have to know how to do it. And the images are typically pretty noisy. I mean, not as noisy as they were years ago when I had a CCD, but there's still noise there for sure. So I tend to use a lot of things like I use Noise Exterminator a lot. That comes in very, very handy. It's an AI-driven noise reduction routine. There's several of them out there. You know, Topaz has their own and so forth. If you're very careful with them and, you know, you don't destroy data or create data, it's a fine line you have to run. But yeah, they don't look, they would look very similar to somebody shooting M31 and maybe taking just a, you know, a very short exposure of it. It's kind of noisy looking, you know, you don't see a lot of that faint stuff that's around it, you know.
Okay. John, incidentally, I should have told you this earlier. You can stop sharing unless you've got something you want to present out of the slides.
Yep. Sorry.
That way we can, oh, that's okay. I should have pointed it out. Let's see, Tarek apparently is going off to work or something. And the rest of us, I think of, oh, except for, who is it, Larry? He wants to know about your observatory. He wants to do something similar, but I think he'll probably try to get a hold of you special on that because he's like envious. Yeah, and I think that's pretty much the chat section. Eric, you're the host for tonight, right?
I have a question and a comment. As far as continuum subtraction, I mean, it's a pretty obvious thing. That emission line is very, very narrow, even with a 3 nanometer filter. If you look at a red filter and the spectrum of red filter, it's a continuum Gaussian curve. So there is definitely something going to be at that particular wavelength, no matter what you do. Now, whether, you know, it's a lot of subtraction, and actually the subtraction process is kind of variable. So
it is.
It's not just X minus Y.
No, there's a whole process to doing continuum subtraction, and it would take an hour just to kind of tutor someone on how to do it right. You know, it's changes image to image. It's different.
All you have to look at the emission on a red filter to know that there's going to be some data there, and whether it overwhelms your HA emission or not depends on the strength of the HA emission. I mean, I published an issue, an image on M31 on HA, and the structure of the HA was completely hidden by the continuum overlap emission. So yes, you have to do that. Second thing, we had a presenter, a couple months ago, that was doing a complete sky map of hydrogen alpha emission. And that was due to be published in February. I haven't really seen it, but that might be a good place to look around.
Was that the MDW survey?
Yeah, I think
Sean Walker and somebody else, I believe, is doing that. And yeah, they did have a wonderful shot of HA throughout the whole sky. But you know, some of these objects are not very strong in HA either. So some of them are only like in O3. But that would definitely be a start. It maybe to pull in, if you have a specific area of the sky you're looking at, maybe you can take a chunk of that survey in that little area and kind of see sort of what it should look like. Sure.
Do you know if that's published?
I don't know if it's published. I know you can go online and you can see some of the images. You can just Google MDW survey and you'll find it. But I don't know for sure. Yeah.
John, when you were talking about the narrowband imaging, Do I start taking it that you don't take S2 in you just use the HA and O3?
Well, I haven't used a lot of S2 because most of the stuff I've been interested in has been these faint planetary nebula candidates, and most of the work with those has typically been HA803. However, if someone is more interested in the supernova remnants, then S2 is surely a good band to also use. I just haven't used it that much. I have used it on a few images, and there was no data there, but like that last one I showed, that supernova remnant, the STDR team over in Europe did shoot S2, and they got a surprising amount of detail, more than I got. I got the original, look of what this remnant maybe looks like, at least the shock front of it, but they got more detail in the S2. So sometimes, yes, it definitely helps. It just depends on the type of object you're looking at.
And you
Alex,
yes.
you see those 2 extra questions that popped up at the end?
Oh, I didn't see those. Get down there. Maybe he can come. Oh, maybe he can come on the show to do continuum subtraction. Is that possible, or would you prefer if we were referred to one of the existing tutorials?
Well, I can tell you there's one individual that I know that has a wonderful tutorial on that, and that's Adam Block. And I think he may have some YouTube stuff on that. I'm not so sure, but he has some wonderful tutorials about that. And he explains it from a science background point of view of why you do it and how to do it. But I came across, I don't know, I think before the show started, I was looking up some continuum stuff, and I came across half a dozen websites that were talking about how to do this.
Start with a Google and go from there.
Cloudy Nights has a lot of stuff about it. There are other YouTube presenters that do image processing that talk about it a lot. I only learned how to do it a couple years ago, and I think I learned it mainly from Adam's tutorials, but it definitely is it takes a little time to learn it, but once you learn how to do it, it really helps you find these really faint stuff that are often hidden.
Josh has asked a speculation here, and like, what kind of scope do you need? His particular question is, would this be a good option for someone looking for something to occupy a Red Cat 51 during galaxy season?
Sure. For supernova remnants, I bet that Red Cat 51 would be a wonderful instrument with a sensitive camera. You just want to pick a large object, something that, because that scope's going to give you a huge field of view, depending upon the camera you use. But yeah, I see images all the time on AstroBin that people have little fast scopes, and they produce these wonderful shots. I mean, I think Bray Falls has a Takahashi, I think it's FSQ 106 with, and he's made some wonderful panoramas, fast refractor, and he does some wonderful work. So a small scope can be used for sure.
Bray was with us earlier this evening. I don't know if he's still here.
I would say don't pick a tiny object with the Red Cat 51. Pick a big object. That's all,
So probably not a planetary nebula.
Well, some are big.
Or at least an undiscovered one.
Yeah.
Because we would have seen it already, probably.
Yeah.
Okay, I think we got them all.
I think we got everyone. John, thanks so much. Great presentation. We always learn something, no matter what we think we know. There's always something more to learn.
There's always something new out there to find.
There's always something. So I made a few notes, and I'm sure other people have, and we're all now going to look it up and say, all right, what have we done wrong? Now we gotta correct this.
Well, we all of us have done nothing wrong, but all of us don't. There's a lot of other stuff out there that none of us know about. That's
Absolutely. So I think we're all set. Anything else? And if not, I think we say goodnight. Everyone, please come back next week and learn all the new things that are on AstroBin. We will be here. All of you should come back as well. So if we're all set, we can say goodnight, everyone.
Hey, thank you guys so much.
Take us out. Patrick, are you ready to show?
Todos.
And my wife says, say goodnight, everybody.